So, coming back to the same lift design, now let me just tell a few things, right, tell a few things. First of all, I talked about zoning, vertical zoning, related to this problem itself, vertical zoning, let us say. Now, let me tell you. So, vertical zoning, one simple way is to do is make lift stop in odd floors or even floors. So, some lift, part of the lift will be operating for odd floor zones. This is up to 16 story you can work out. Now, so odd, lifts are being only odd floors or even floors. Now, what is happening then? Floor height, floor height is now twice, floor height is twice, and number of floor to be served is half. Number of floor heights, So, I can actually, so you can see that your round trip time will reduce down, because n minus the n comes in, n has become half. So, round trip time, but TV is more now. Not TV is the one floor. Yeah, TV will become more and TF will become more. TF is the one floor jump term. Now, the floor height has become more, right. So, this we are calling it dF, height of the floor divided by velocity. Velocity is same. So, distance of the floor, floor to floor distance, that has become double. So, that is the only thing. The other situation that you may come across, is, right, I will come to vertical zoning further. Normally, ground floor lobby to the first floor height is more in many places, hotels and similar, because you will have certain things, receptions. It is even in offices, you will see modern offices. So, ground floor height is usually more, ground floor height is more. So, if your ground floor height is more, rest all floors are all safe, right. So, if it is more, then what you do? Additional height of the ground floor. For example, typical DF floor to floor distance, let us say, is 3.5 meters. Let us say the ground floor height is 5 meters. Then you have got now 5 minus 3.5 additional 1.5 meters, right. Now, that additional 1.5 meters will be travelled at constant speed. So, that time you got to add twice while going up and going down. So, that time has to be added into the round trip time. Such kind of small details you have to handle depending upon the situation. Population different is not a problem, right. And then if your lift acts as express lift for certain distance, like in zoning, let us say it is express, express lift for certain distance, express zones, vertical zones. So, express for certain distance, certain height, certain floor height, certain floors, that distance you will take at constant speed. So, it goes up to, let us say, 8 floors as express. So, up to 8th floor height, it will go at constant speed. So, you like it is like having a floor height different, it is not going to stop there. So, it will straight away go to up to 8th floor, then it will, then our formula applies. So, total number of floors will become not 16, but it will be actually 8 plus 1, because 8 floors, let us say, it is serving as passenger below ground floor. So, there is 9 floors to be served, and ground floor height or first top height will become 8 into floor heights or floor heights up to 8th floor. So, that would travel at constant speed, and you can see that round trip time will now reduce down. If you had passenger lift, then it would have gone to all the 16 floors, probability of number of stops, everything is related to n. So n has become half practically from 16 to, let us say, 9, right, 16 to 9, and that is one aspect. Second aspect is it is traveling at constant speed for that distance, otherwise it would have jumped, that many number of there. So you can see that round trip time I am reducing down by making it express. And if you calculate out the round trip time for the up to 8th floor, this is also less. So you can see that you can save on to the time of travel comfort, in the sense that waiting interval is less, which is comfortable. People like, people dislike to wait, and also space can be utilized. For example, if it is some shaft is up to 8th floor only, so top floor I can use the space for my functional purpose. So this is one aspect, and problems, there are problems of this, problems will be there, some problems are there dealing with this sort of situation. Okay, so that is one thing. So for unequal floor heights, additional distance is covered at contract speed. For speed more than 1.75 meter, right, per second, floor height less than 3.3 meter will not enable contract speed to be attained. So if the speed is low, speed is, speed is high, and I need certain time to arrive at that speed, right. So you can show that if it is accelerating and retarding at a constant acceleration, usually acceleration rate is constant, retarding in the constant, accelerating and retarding in the constant rate, I need some minimum height, because otherwise within part of the, it will just start accelerating, somewhere it will have to start retarding if the height is less. So there is a minimum. Typically if the speed is, velocity is, let us say contract speed is 1.75 meter, the average velocity would be 1.75 divided by 2 during the acceleration period, because it starts from 0, and that is what is used in our V equals to u plus ft formula. Basically you assume the constant acceleration, and you can derive this on this basis. So basically my average speed is v by 2 during acceleration time, and during retardation time also it is, deceleration time also it is v by 2. So if it is 1.75 meters, I need at least 1.75, somewhere around 1.75 meter must be the distance I should cover with this speed. With this speed, what is the distance I got to cover, because the time would be the distance which I start from 0, so it is half ft squared. No, time is not the issue. Actually average velocity is this. You can show that if it is less than 3.3 meters, it will not reach actually that speed. It will not reach that speed, it will have to actually start decelerating even before it has reached the constant speed, even before it has reached the constant. So it is in 1 second it will reach in 1.75. So, in that case it will reach half of 1.75 velocity in one. Constant speed is this. So 1.75 meter it will take actually 2 seconds, but time is not an issue, because acceleration, distance I should be able to find out. I should be able to find out distance basically. I can find out v is acceleration will be velocity is average velocity is v by 2, and right. The distance required to arrive at that is or distance. Two things are unknown: acceleration and distance. So anyway, so that one can show that possibly you need. One can show that you need at least minimum distance before it can reach to the acceleration time. I mean, you cannot have very high time for accelerating, short time. I mean, it cannot accelerate to that, because the velocity has to be achieved 1.75 meter per second. Now you cannot, minimum time required to accelerate to that. that that would possibly limit it to 3.3 meter. So anyway, this is one issue. This is one issue. So floor that you can calculate this out. Now second issue is that's contract speed to be attained in one floor jump time. So it's okay, it's all right. We can see that by calculation you can check that how we are calculating, but the acceleration rate has to be known. If it is too fast, then obviously it can reach at lesser height, but practical heights may not make it feasible. Okay, but the second issue is important issue. We made certain assumptions during this derivation. We derived with Q is equals to 80% capacity. Now this is valid when I have sufficient rate of arrival, and in a way rate of arrival matches with the rate of service. People come as soon as nearly 80% or 90%, like on an average 80% people have come, it goes. If the rate of arrival do not match with the, if it doesn't match, if the rate of arrival has to coincide with Q by RT. Q is the capacity divided by round trip time. During this period of time, Q is the capacity, so that many number of people should be coming per unit time. Then in RT time, because RT time lift comes back, or waiting interval, I can say, it has to match actually. Supposing it's a single lift, by the time it comes back, same number, more number of people should come. If more number of people come, their waiting interval becomes more. If less number of people come, then it will go less than 0.8. So my formula changes actually, because my HNS depends upon Q itself. So if less number of people come, actually S will become less, H will also become less. So my formula is not, then this is not valid actually, this is not valid. So this is assumed as a steady situation, flow is steady. People are coming, they are boarding and they are able to go. So this is with respect to for a single lift. If there are more number of lifts, my waiting interval, Q divided by waiting interval must match with the arrival rate. The arrival rate of people should be matching with Q divided by waiting interval, because Q is the capacity. So during the waiting interval, Q people must come. But this is not the case. So otherwise you have to get S and H by trial and error if it doesn't match. For example, you have, supposing you have decided that there will be more number of floors than rate of arrival, you have to match that. If you have decided that your more number of floors, more number of lifts, then that's actually required. You will find that less number of people are traveling every time, because there are too many, so waiting interval will get reduced. Round trip time is fine. We have decided on, so this matching the steady state, this formula is valid for steady state situation. If it is not so, then we calculate out through a round and trial and error procedure. Let us see what we do. Supposing I have a rate of arrival, 120 people arrives in 5 minutes peak period, right? So for the same case, for the case that we had 141 earlier, that problem that we did, we found out our round trip time was 140 seconds or something like that. We found it out. Remember, we found out floor of reversal was S equals to 9, floor of reversal was 15.3 and S was 9, and then TV was given as equals to 1 and TF was 5 seconds. Remember that we had, and Q is equals to 12.8, right? That data was there. So based on that we calculated out, it came out to be around 140 seconds. And we said if I have 5 lift, 5 divided by 140 gives me 28 is a waiting interval, right? So 28 was a waiting interval, it came as a 141 or something like this. So let us say in that case, this is what I have designed the lift with certain assumptions, Q is same and arrival, population, based on population and all that I calculated, but actual arrival rate is 120 people in 5 minute peak period. In other words, the arrival rate is now 120 divided by 300. So arrival rate is 120 divided by 300 seconds is equals to how much? 120 divided by 300 is how much? 30 12. So, it is actually 1.2 divided by 3, right? 1.2 divided by 3, 0.4. Numerically 0.4 per second. Arrival rate is 0.4 per second, 4.4 persons. Numerical is fine because we are only doing calculation purpose. It is not 1 per, no, it can be, I mean, theoretically it cannot be less than, but for our calculation purpose, we are saying 120 people arrive in 5 minutes, which means that 120 by 300 is a number of people per second. So, that is the arrival rate persons per second actually, 0.4 persons per second. Now, I have actually assumed in, I found out the waiting interval as 28.3 because it was 1841 I think, 141 divided by 5. So, exact calculation or something like the 142, yeah, something. So, that is 28.3. So, my actual arrival rate is 0.4 multiplied by 28.3, while my assumption is Q was 12.8, calculated on the basis of 12.8. So, H and S should change, then H and S should change because Q is equals to now 0.4 into 28.3 and which will be actually equals to how much? 11.32. Yeah, so 11 point, so it is less than that, and all my formula is based on to the power Q. Now, power changes, the value would change significantly. So, therefore, I must relook into my H and T situations, it will change, and this we do by trial and error procedure. So, what is the trial and error procedure? First assume, okay, my round trip time is equals to 130 seconds. What I do is that I assume that 120 people are coming. So, waiting interval, what should be my waiting interval? 28.3 divided by no, 136, because 130, this is T will also, of course, it will change, and okay, what I am doing is instead of assuming 1 for T, I am reducing it down to some value, right. So, basically new I have to get assume that waiting interval is
So, the handling capacity came out to be 13.6%.
yeah, that is okay, but no, not 13.6%. You see, waiting interval is how did we calculate out? Waiting interval was yeah, 136 people we take. We took 136 people. 136 people, 13.6 is the people, 6%. That means out of 1000, 13.6%. So, in 100, 13.6 in 1000, 136 people. 136 people. That's what that's what we calculate out, handling capacity we calculate out. So, it was handling actually 136 people, but now I want how many people to be handled? 120 people. Waiting interval was waiting interval. So, I want to find out the new waiting interval, and then I will go back to, because if 120 people are coming, right, I calculate actually I assume that 136 people will be handled in 5 minutes, but now I am handling actually 120 people in 5 minutes. So, 120 divided by 136 into 28.3, this should be my, this can be my new waiting, I mean actual waiting interval should be, even if my waiting interval is 25 seconds and provide a Q for that. So, Q would be 120 second divided by so 10 is good enough, 10 itself is good enough. That is what, if I take that round trip time 13. So, I was handling actually 13.6 people in 5 minutes. I should be handling 120 people in 5 minutes, right. That means, in each trip I can take less number of people, and if I take less number of people in each trip, assuming the waiting if I take, because it will have less number of stops, so waiting interval also will reduce. So proportionally I am reducing down my waiting interval, because my S will reduce, H will reduce, RTT will reduce, and with 5 lifts T will also reduce. So I am assuming a reduced T and correspondingly finding out the new Q. H is, then I find new H, I find out new S, I find out, and my RTT comes out to be 122.8 for 5 lifts. T comes out to be 4.6, which is not same as 25. It should be sufficiently close at least to the last figure. Should come close to 25 or 25.1 or 24.9. This is not sufficiently close. That is what is thought, that it should be as close as possible, right, so that your arrival rate and this matches. So in the next trial, what you do, difference is 25.4, 25 minus 24.6, right. So what you do is you reduce this 25, this is the difference. So waiting interval you reduce twice of this difference actually. This is 24.6 is lower. So I must, because if I make it 24.6, it may come still less. So what I do is I reduce it by difference, go still below that 24.2, find out the number of Q, repeat this process, and I get started with 24.2, comes out to be 24.1. So they are more or less same. It should come as close as possible, only on the 1 decimal point. So the thing is that now if I choose 9.7 as the capacity, or I might choose a capacity 9.7 divided by 0.8, that would mean basically the capacity will be, the actual earlier I took 16, now this will be how much, 9.7 divided by 0.8 would be how much, 1, 12 or 13 capacity possibly lift will do my job. So if I provide 13 capacity lift, my round trip time and arrival rate will by and large match. Now this was arrival rate earlier was based on essentially when I find, basically I assume the lift size of the lift, starting lift size I have assumed, Q value, 16 size, and then I calculated back everything, right, I have of course choice of making Q as a choice or number of lifts as a choice. Supposing I have already decided upon my space for the lift well and number of lifts that I will be providing, the capacities I can play. So this kind of basic idea is that the formula is valid for arrival rate matching with the service rate, and we can make it as close as possible. So instead of using 16 capacity lift, possibly I can use 13 capacity lift, and it will do serve my purpose. So that's the idea. So that's how we find out. We find out the number of lifts with assumption of a given capacity. Now and then finally do fine tuning to a better capacity or smaller capacity or larger capacity as it might require. So that's how you find out. Lift, of course I will talk about lift arrangement a little bit later on, but let us understand this, that this we can do by simulation also. Same procedure I can do by simulation also. Now for example, this is for a case of single purpose office, all at same timing. Now you want to improve the performance of the lift, or you require less lift capacity, something like 40-50 story building. Normally of course occupancy, there will be usually won't be having similar kind of occupancies, or might have residential occupancies. Now if it is residential, then the problem becomes less, because it will not be, all people will not come same time, right. The arrival rate would be quite different. So one has to apply their mind, but this is the basic kind of a concept. There can be a situation where I may have lot of random interflow traffic. Supposing I have same office serving from, its floor area is in 3rd floor, then maybe at 7th floor, or third floor to fifth floor or seventh floor of the same office, another office. So you can have random interflow traffic depending upon the situation. In such cases, when you have random interflow traffic, you can actually, it is simulating is better. It is not only upgoing traffic, but it can be up and downcoming traffic also. You may have to design the number of lifts for such situation or find out lifts for such situation. But that's not usually common, but you can have those situations as well. All right, it is possible to simulate this also, Monte Carlo simulation, by assuming this as a Poisson's process. What is Poisson's process? What is Poisson's process? Well, Poisson's process is usually used in waiting line situations, right. So what you do is you assume the rate of arrival of the people. You know, when you are serving people, you know, they are arriving and you want to provide service. So that's a waiting situation, isn't it? So if I know the rate of arrival of the people, then what we do is in Poisson's process, what we are assuming that they are arriving at a very, we consider a very small time, delta t. Yeah, lambda is a waiting interval, I mean a number of people arriving, and we consider small time delta t such that not more than one person will arrive during that period of time. Never can happen, you know. So such small delta t that not more than one person will arrive at that time. Now arrival of person, then we consider it to be success, while not arrival is failure. So this becomes a binary situation, you know, or binomial situation. Now if you recollect binomial distribution, you know, statistical binomial distribution, that deals with such situation, probability of success or probability of failure, right, probability of success. So 1 minus probability of success is probability of failure, or 1 minus the other way around, or vice versa. So only two situations are possible, success. So what we do is, you see, Poisson's distribution is a special case of binomial distribution, when actually the you know, like it depends upon, I mean, when, you know, number of trials tends to infinity. So we'll see that actually. Just see that probability of x success in n trial is given by, I'll just give you, recollect this actually. So in Poisson's process, what I do, we assume lambda person is the rate of arrival, lambda per person per unit time is the rate of arrival, lambda t is the person arriving in time t. Consider a small interval delta t. There are n such trials. Then how many number of success in n trials? That's what the binomial probability. Okay, let me just go back to give simple example to you. Supposing I am dealing with a situation of a die, right. So there are 6 outcomes, and I want to find out probability of finding 1 in 10 trials, right. So probability of finding 1 in one trial is 1 by 6, right, and probability of finding in one trial only 1 and not finding any others. So I should not find, you know, 2, 3, 4, 5, 6, I know all others. So joint probability of finding only 1 and not finding all others. So that would be 1 minus 1 by 6 to the power 5 joint probability, because other 5 should not occur, right, and 1 should occur. So that's what it is. So now in 10 trials, now that means I can, what is a, you know, this becomes a situation of combination, you know, NCX. I can find out in the first trial I can find 1, or second trial I can find out 1. Now this would be actually related to, so if I say this is the probability p to the power x, that means finding in x trial. Now this is this is wrong. This is 5 by 6 is the probability of not finding all others. Not now in 10 trials I should find, that means in 10 trials I should, the probability of finding x number of or 5 number of 1 in 10 trials. That is what I am trying to find out. Let us say 5 ones in 10 trials, that is what I want to find out. That will be a binary. So, if I have to find 5 in 5 times, then 1 by 6 should be joint probability of finding 1 by 6 5 times, and 10 minus 5 other 5 cases I should not find anyone. Anyway. So, this is the joint probability of not finding them, and this I can arrange. First 5 I can find, or any 5 I can find. So, that is what is given as 10 C5 would be the case. So, this is the situation of binomial distribution. So, when n tends to infinity, p tends to be small, then this can be actually approximated to Poisson's distribution. This can be approximated to Poisson's distribution. I think I might be having, okay. I'll just, maybe I might be having something more related to this. So, I think we will discuss this simulation aspects in the next class. We will have a break and take some questions from you, and then the binomial distribution related we will discuss in the next class. Okay. So, that is what it is.